Ready? Good afternoon. Oh, it's not on. So today we had the first session of labs in the actual nano lab. It was quite a good experience, I feel, for the students who came. But the problem is the students came without any idea. It was like they came like a free hand walking in. That I don't expect that. Something has to be done before you come. Probably one reason is maybe you didn't understand what I put in the Moodle. I thought you will do you will understand yourself. Looks like not. Okay, let me clarify this next 4 weeks of activity. What is that? All of you? So the idea here is we are planning to fabricate comb structures. These comb structures could be made up of aluminium or gold on silicon or on lithium niobate or sometimes glass, any of these substrates. Okay, so today batches did on silicon. They used aluminium electrodes. So our ultimate aim is the first layer is the substrate, which is of this type, and then above which there will be a coating of metal, which will be gold or aluminium. With aluminium, gold, or only these two. But usually, when there is a gold, we will have a thin layer of chromium also. So chromium is a good adhesive for gold. So there will be double layer. Above which we will do the lithography, and we will be making these kind of comb structures and just drawing the sideways. So this will be gold or aluminium, gold or aluminium. Then after which we will be sputtering, coating a thin film of zinc oxide like this. Okay. Then there are electrodes to connect wires. We will be then doing an IV characteristics of this fabricated device. For different values of current, we measure the voltage. Now, as I told you, the zinc oxide can change its conductivity when you shine UV. So, with presence and absence of UV, we will, like how you did in the COMSOL to do the IV characteristics, we will really do an experiment. So, the structure could be like this, or some students may have a structure like the substrate. Then there is a contact, could be metal or the silicon itself. Then the zinc oxide. Then again a contact. So this is also, we call it as a Schottky diode. Okay. So we will measure the IV characteristics of this. Either we will have this or have this finally. Okay. So this overall in the next few weeks, the first layer of making the samples and coating the metal, the first step is already done. That's why I said step 1 and step 2 is actually preparing the samples. So mostly preparing the samples we already do, and we also did the coating of aluminium or the metal for you. We don't do it. Some step 3 we will start. Now step 3, step 4, step 5, it goes like this up to 8. But what happens is, our clean room can only maximum accommodate 4 or 5 students. But I am now sending 8 students in a time. It's like a really lot. So only 8 students can go at a time. So what happens to the other students? But you don't have that much time. This is not a really real FIB project, or it's not a postgraduate project. We are doing some assignments for your subject. So the idea here is, I'm going to, already we have the other steps also. I have some samples already done. You understand? Already we made the samples, some of them. Say suppose one group goes inside this step 3 to do this, the other groups may do some other steps. So every week if today, if say this week, if a group went for clean room, then they will do some of the steps the next week. Okay, you understand what I'm trying to say? So every one of you can get a small initial from the demonstrator, whoever was there. I'm thinking to give some certificate as an appreciation that you attended the whole thing. Okay, which can be maybe useful for you later on. So, and also it's.
So are the steps independent of each other?
Pardon?
Are the steps independent of each other?
Actually, if you say in a real ideal case, it has to go one by one. But in the real fact now, it's not possible. 63 students, we cannot do it this way. So what we did is, I thought a better idea is to organize in a way such that some of them we finish it already. And you do some students may directly go for step 7, probably no. This 6, 5 and 4, 3, 4, 5, 6, these steps will be like in cycle. 7 you cannot do because until you finish the whole thing you cannot do the 7. 7 is the last measurement step which you may be doing in the week 10. Okay. So after, from all these things you will have the results. Now the results are to be accumulated. You should record all the results in these activity sheets. You should have it with you whenever you're coming to the lab now. I'm just taking an example of this clean room. So if you see here, there are some questions I'm posting here for you to make observations. For example, the last 10th step says a microscope image of a typical fabricated device. That means once you finish all fabrication, I want you to take a picture of it. That's the result of the whole thing. Correct? So when you are writing the final report, these 4 sheets, you combine them together. So already you have results and you know the methods. What is left is the discussions. So the mini project, what I mean here for the 12 marks is actually combining all these things. In addition, probably 6 marks of the discussions what you're going to do with the results you have. Because I'm not going to discuss about the discussions part. I'll be only telling about the results what you have. So the job from your side is to actually do that. Okay? So that's the mini project marks we have. So basically we don't really do a project. The project is actually we are doing from this week. So already we are doing it for the week. Nobody will tell you to go and do a project in week 12 and submit the report by week 12. It's a very foolish thing. So that's how we're actually trying to do over the next 4 weeks of time. Okay, as I mentioned. This should be clear for everyone. Yeah. So don't come blindly without any idea about have a look on these steps. I know it's a little hard to understand, but just see that there are some steps. When you come there, I will again explain you all these things. Okay. So that's about the lab I want to say. So each of these lab carries 1 mark for the lab itself for doing the observations. And in addition, we have 12 marks for the overall report. That's different. So totally it's a lot of marks. In another way, if you see, the good point here is the 50% of continuous assessment, you have a lot of scope to get easy marks, basically. Quite easy to get marks in this way. So that means you can expect the final exam to be tough. They give you a fear, then only you feel. Yeah, tell me, any questions? Yeah, questions? Yeah, ask me something. No, okay. Want to ask private later?
It's last semester, so please don't make it.
Coming in?
It's last semester of long class, so please don't make it.
Oh, okay.
I agree.
Okay.
So what about the industrial?
Industrial research, we are trying to move on the next week after the midterm break. To be on a day, 1 day.
So like, are you capping the amount of students, or are you capping an amount of students, or
The whole class has
Whole
to go.
class.
3 marks. Okay, 3 marks is actually for the attendance itself is 1 mark. You go to the result, you get 1 mark. And then I'll ask a small quiz, 2-3 questions based on the visit. Just click the answers like what you do every week. You know, when you answer the quiz, I always also monitor by sitting in my home. I see what all people are answering. I checked it. I see some students answer in 10 minutes. Click, 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 click. Finish. Okay. So that's like a big quest. Okay. Okay, there are some issues with question 3 and 4, but the recent one has no mistakes. I will work out the answers later. Okay. Right. So coming back to the topic, chemical vapor deposition. So, as I discussed, there are several steps of microfabrication. One of them is the lithography. Some of the students might be really appreciating today. You might have seen it very clearly, and by the end of this week, many of you will be very clear. Next 2 weeks. So, apart from this, one of the very important deposition technique is the chemical vapor deposition. So I'm going to discuss about this first, the principles, and then I will give you 2 examples of chemical vapor deposition. One is our own favorite zinc oxide what we do in our lab, and also the silicon which is there in the slides. So as I discussed yesterday, the last class, I started drawing about the CVD. So the CVD system has a quartz tube. And this quartz tube has heating elements at the borders of this. At both the sides of the quartz tube, we have heating elements. And these heating elements are controlled by some PID controllers. So the amount of current you flow to these coils will determine what is the temperature. Okay, you can control the time, how much temperature is required for how much amount of time, and so on. The another important step is one end of the tube usually consists of some airflow or some gas flow. So more than 1 or 2 gas cylinders may be connected. For example, for simplicity, I just take only one. Say, for example, maybe 2. We'll have 2 of them. Okay. So gas inlet 1, gas inlet 2. So this is usually one of the gas. We call it as a carrier gas. So the carrier gas is usually an inert gas. Could be something like argon. So argon is an inert gas which does not react. So usually the flow of this gas is higher than the reactor gas sometimes. So the carrier gas actually accumulates the whatever the reactions that needs to happen, and it transport this reactor or whatever the molecules of deposition along with that. So when the flow happens, it starts from one end and finishes in the other end. It's just the flow of air. It's something like somebody's blowing in the pipe. Yeah. So what they do, the source, the material source which has to be deposited is usually kept in form of pellets. Pellets means small tablets, tablet type shaped materials, pellets, or it could be in powder form. Okay. Usually it is kept on we call it as quartz board. Sometimes ceramic board we call it as board. Okay. So now since we are heating, there are a lot of heating coils all around. Say this temperature what we maintain some high temperature like 700 degrees centigrade, 1000 degrees centigrade, something like that, a very high temperature. Now, this temperature should be high enough to melt and vaporize this material. Okay? Yeah, guys. So when we are vaporizing this, so the vapors are emitted out from here. Okay? So when the vapors are emitted out, the carrier gas the carrier gas, the argon molecules, we get mixed with this vaporized material. So along with the flow of the gas, these particles are getting transported in the tube. Can you realize that? Yeah. Then what happens? At certain edge, we place the substrate which we want to coat. Say for example a silicon substrate. So these materials, when they pass through, actually they deposit everywhere. Okay? So it deposits here as well. These particles just start depositing. So sometimes if the one end of this tube is open, what do you comment about the pressure here? Anybody? If one end is open, what do you comment about the pressure at the open end? Atmospheric pressure. Atmospheric pressure. So here the pressure is higher because there is a flow, but here we don't have anything. So the pressure maintained is an atmospheric pressure. So the flow is always this direction. The pressure is low this side. Okay. Sometimes what we do, people also connect a vacuum to this. So they will keep on pumping the things, whatever is coming up. So one end it is vacuum, low vacuum it is pumping all the molecules. The other end you inject them. Now in certain cases, there could be two or another few more inlets of gases could be there. These gases are called reactant gases. Okay. Example, something like oxygen. If I want to oxidize something inside, certain things, if you want to oxidize and then deposit that, in that case, the oxygen molecules are also flowing inside now, and the vaporized material combines with this oxygen, they get oxidized, and whatever is flowing now is an oxidized material. Can you get this? And then you deposit on the substrate.
So if we move the substrate along the tube, what will happen?
Okay, you move, that's a lot of experiments can be conducted. Suppose if you go more closer, there could be more concentration, be more far, there will be less concentration of these reactants. So, a lot of parameters are there. You will see that in a while. Okay, so the overall principle looks like this.
So the other end is open, right?
Yeah.
Isn't it kind of dangerous?
The other end open is one kind of
But is
CVD.
it
It's called
dangerous?
atmospheric CVD system.
Isn't it dangerous? Like, because you're...
These vapors, yeah, very
Yeah.
good question. Yes, I should answer this. Actually, it is, that means you have like an exhaust inside your lab, right? You're always producing some poisonous gas. Actually, in that case, this should be vented out carefully. Or what people do, this is actually a very good question. I want to answer this. Sometimes what happens, we actually have some wash glasses which actually will have some liquid, so like solvents or some water, and then there is an outlet like this. There could be many such wash glasses will be attached. So what happens when the gas now enters this, the particles, they get deposited in this water, then we can safely dispose it. Okay? Yeah. But if the exhaust is very less, we can actually just make it outside.
So can we just push the exhaust back into the system? This is only argon and the...
No. If you will put back this here. Yeah. Then again, what will happen? We don't maintain the pressure. Yeah. Okay. This combination of these gases, the flow of these gases, and the amount of the substance what we keep, they all are having some empirical formula. They all are related. If anything minutely changes, we won't get the actual deposition. I will show now examples of that. Okay, this I explained just to get the feel of the overall idea about CVD. What does that mean? Now, so metals, organic materials. So as I said, three types: atmospheric pressure, low pressure, and plasma enhanced CVD. There are three types. So what I discussed now is probably two types. The first two types, plasma, I will say later. So what I explained now, as where it's written in the text here. So CVD involves flow of gas containing diffused reactants. The gas that carries react called carrier gas. So what all I just said is there in the text. Now the reactors could be sometimes vertical or horizontal. Probably in the lab I was showing students we have the horizontal reactor. Okay, so I'll come back to this. Okay, some of the very important aspects to think on CVD. Not much of physics as well, it's quite simple to understand. Now if you see, so we keep the substrate, something like this, and let's zoom only there, say silicon substrate is there. So when we have the flow of these reactant gases, basically there is a flux of these reactants created. What is the flux? Flux is supposed, you know the magnetic flux or electrical flux, you can understand. Okay, same even in a chemical terms, when you have a mixture of vapors of chemicals, the concentration, distribution of this concentration of these vapors, we can say in terms of flux. Yeah, suppose if there is any ammonia gas or something in this corner, that's the source. So there is a large flux of that ammonia gas at that corner, but there is nothing at that corner. Can you imagine this? So such the flux is created along this region in the whole tube. Okay. Now what happens? Very, very important point. Very, very, very important point. Exam point of view also. When you have a flow of gases, what happens is you can also realize in a true experiment. I keep this object here. I sit and start flow like this. You can realize there is an air flow on the top. There are certain regions definitely there is no air flow. Can you realize that? Can you imagine that?
Yeah.
Because of an obstacle on the surface. Can you imagine that? When a flow happens on a surface, there are certain regions, very small region where there could not be any flow of air. That's because of that obstacle here. So because of this, a boundary layer forms. Okay. So when there is a flow here, now assume this is the substrate here. You kept the substrate. Below this is the substrate. Okay. The black thing here is the substrate. This is also the substrate. My picture. Now we are seeing that part alone, and the substrate is kept here now. Substrate is not shown. Just above the surface of the substrate, because of the edges effect here, edge effect of this, there is some region, there will be no flow on the substrate. Can you imagine that? That region where the reactant flux is very minimum, the gas flux is very minimum, we call this as boundary layer. Do you get this? What do you mean by boundary layer? What I mean by boundary layer? Let's give a symbol for that as sigma of x is the boundary layer, where x indicates the direction. Say for example, if this is 1 centimeter, then sigma of 0.5 centimeter is this. You understand what I'm trying to say? Okay, I'm going to repeat again about this. This is very important. I can assure you something I'll ask in exam about this. I keep a substrate here. Okay, I just zoomed there. So when there is a flow of gases, these reacting gases, what happens is because of this corner here, the gas, whatever the flux, what is it? There will be a small region, some region here, up to some region here, there will be no reactant gases, and the boundary layer forms like this. Yellow X. Now, this boundary layer, people have already identified a formula for this. To identify this formula is actually the Reynolds number divided by this is actually given by x divided by square root of. Okay, again, how do we get these formulas? These are all empirical formulas already derived by some experiments. Okay, so Reynolds number. Have you heard of this Reynolds number? Mechatronics students would have it, mechanical students.
So it's basically if you have a block and there is a flux, then there will be a certain small region that is a vacuum, right? That has
Yes, exactly like vacuum. Yes, what he says is correct.
It's like a car traveling very fast. Like
Yes, yes. But, we cannot say fully it's not a vacuum. There is no reactant flux there. So these, whatever the reaction that has happened, right? The mixture of these gases are mixing with some material and then they are flowing for deposition. But what happens is, some region, those materials which has to be deposited is not there.
So what if we just rotate the substrate?
We can do all these things. We can rotate, we can keep it slanted, yes. But generally you are going to have, when the flows touch the first edge of the substrate, we get this problem. We have done quite a lot of experiments even in our lab on these matters. So Reynolds number describes whether it is how fast is the flow. Okay? And this Reynolds number is can be calculated by rho LV by mu. Rho is the density of the gas, L is the length of the tube or channel, V is the velocity of the gaseous flow, and mu is the viscosity of the gas. Now this is a very, very popular formula for mechanical engineers. The Reynolds number, it describes the kind of flow. If this number is very large, we say it is a very if this number is very small, we call it as laminar flow, very mild flow. If this number is very large, in terms of thousands or 10,000, then it is like a, what's the actual name? I'm getting in mind now. Anybody see? Anybody? What do you call that flow? No idea. Huh?
Turbulent
Turbulent flow. Turbulent flow. Yeah. So we say if that number is very large, we call it as turbulent. And if this number is very small, we call it as laminar flow. So this Reynolds number depends upon, you can see, it's mainly the length of the channel, of the, here in this case, the length of the tube, the kind of gas we have. That's the which is described by the density and viscosity. How viscous is the fluid? And this velocity depends upon the flow what you set. Today, some of the batches you came there, I showed you there is a mass flow controller in the sputtering machine. I told you that there is a cylinder connector over attended today. Yeah? So we set the flow. So the gases which is entering has its own velocity and its own Reynolds number which is coming inside. And you know what is this x. So x is actually defined by, again, where is the x? If you see this picture, this is x. There is certain distance which is actually along the length of the substrate. So the this boundary layer is actually depends on this formula, which actually depends on so many other parameters. If you see, do you understand? The boundary layer now depends upon so many parameters. Depends upon it depends upon the substrate X, or it depends upon the density, the length of the tube, the velocity of the flow. There's a lot of parameters of that. Now, suppose I'm trying to do some fabrication of some electronic device. Say I have a silicon substrate and then I'm trying to do some, say, diodes or something. What happened is I keep this in my CBD system, and what happened is I expect that some devices will develop here. But what happens is, say, suppose this region had a boundary layer. Eventually, I will not get any device in this region because there was a boundary layer. I don't deposit anything there. Okay. So this is so very important to have an idea about this boundary layer and things like that when the deposition is done. And furthermore, one can also give the about the surface of the substrate. What can be the concentration of? So, if you see here, this. What we are going to deposit here, the thickness of the material or what we are going to deposit here, it depends upon the number of molecules you are going to put in there, or the concentration of the material what is being deposited there. which can be measured in terms of number of atoms basically. So there I have already an empirical formula also has been derived. Again, if you see we have the diffusivity number, and Ng and Ns are the constant. I'm not going to ask any questions on this, just for an idea here. Ng and Ns says the concentration of the reactant at the top of the boundary layer, where Ns says as the concentration of the reactant at the substrate surface. So the boundary layer top is this and this one. So this boundary layer, what I want to say is the boundary layer makes a very big significant effect on what is going to get deposited on the substrate. It's very important one. Now what I'm going to do, instead of going and saying about further on this mathematics and chemistry, I'm going to say our own experiments and our recent work, which will be very interesting. So one of the very important, keep on talking about the zinc oxide every time, because that's what I was working all the time for the past few years. So like silicon or germanium, all these have a very, they are very good for electronic devices. There are other materials like the zinc oxide have their own special properties. For example, zinc oxide emits green light, can be used for making some green LEDs. Okay, and at the same time, zinc oxide also can absorb certain wavelengths of light. Again, it can be used for sensors as well as for many solar cell applications. Quite a lot of solar cells have been made. So it's a very key material after the silicon and all these class of materials. So we were trying to use this kind of a CVD system to make zinc oxide nanowires. Okay? Instead of just a film, we wanted to make wires in nanostructures. I told you why people go for nano dimensions. Yeah? Did I tell you that? We go for nano, when we go for a nano dimensions, the surface to volume ratio increases. The same cake example I told you, when I take the entire film, if you now make smaller regions, you have more surface for reaction. Can you imagine that? If this was a complete film, it's a complete box, then you have 4 surfaces only. Say the same box I divide into many small pieces of nanostructures, then have multiple surface for reaction to happen. So this can enhance more emission properties, or it can enhance the sensing properties. So it is used for sensors and LEDs, and that's the world is getting revoluted for this. So one of the important aspect in the, probably this research is getting saturated also, because people have already established making nanowires of zinc oxide in particular very well. But what we were trying to do in our laboratories, where we wanted to, we are not material scientists, we are electronic engineers, so we wanted to exactly make the chip, exactly we want to make the nanowires in a particular point, and then finally it should work. That's what's the final. The material scientists, they will make the nanowires, and then they will measure in something, and they'll say, oh, we did it. But we have to, our job is to make it electronic devices, it should go to the computers, or mobile phones should work basically. So in that cases, we need to have very established system to make that. That has repeatability. Don't get confused directly in opening some journal article and discussing here, but this is out of more than the examples what is there in the book. I would prefer to use my own experience. So what happens in making a zinc oxide nanowires? Okay, listen carefully, it's quite interesting. When we make a film of the zinc oxide nanowire, any material, whether it will be zinc oxide or anything, if you put any thin layer of any material, if you heat them at very high temperature, we call this process as annealing. You know what will happen? This continuous surface, they get a crystalline surface. This will break into small pieces of nano dimension. We call this as annealing. You get this point? When you heat at a very highly elevated temperature, You make a very thin layer, say a 5 nanometer of a gold, 5 nanometer. We have machines to do that, 5 nanometer of this. And we heat that at 400 degrees, for instance. The materials we don't go to the evaporation temperature. We just like 500 or 400 or 500. In that cases, the materials structure, surface, crystalline nature, something like this. Okay. So basically what happens, when I'm going to heat this, my surface is going to have, if I see the top surface of this, from the top, it actually has so many, this kind of small, I'm actually drawing in a very big scale, but they are very closely packed, okay? So these are all zinc oxide structures. Say I use the silicon, on the silicon they are spread like this. I first made a film of zinc oxide, and then I heated it, it becomes like that at 400 degrees. Okay, let me take an analogy. So for example, basically if we go to another country, for instance, or a very unknown place, you do not know how to speak to other people, but suddenly you find a person from your own place or own country, okay, who can speak your language and who can eat your kind of same food. Immediately bonding will happen. Yes or no? Everyone, we are humans. Because we are very happy to, because we need a help and we want to have a good bonding. But probably after 2 months or 3 months, we may fight with that fellow and go away. That's a different thing. But the bonding, I want to say, we can get it immediately. That's the nature. Same thing. So in that case, both were same people from the same place. That was bonding. So here also, I have a zinc oxide spread over on the surface. So if I now send some vapors of zinc oxide, say some vapors of zinc oxide are spread over all these things. So these are all silicon. The rest of this place is silicon. Only these dark regions, I will say these are zinc oxide. Okay. Let's say the dark regions are all zinc oxide. Now what will happen? Zinc oxide and zinc oxide are same place. They will bond together. They like to stay together. Okay. So the addition of the zinc oxide vapors compared to silicon, it is much more better or strong with the zinc oxide itself. Do you get this? Yeah? Do you get this? What I'm trying to say? No!
Can you repeat?
I said, I have now annealed it and this, the structures became like this. So imagine that this, we have it on the silicon wafer itself. If you go to the microscope, you see a lot of small structures of zinc oxide is settled like this. So what I'm trying to say now is, I didn't go into CVD yet, I'm just explaining something before I go to the actual topic. So if I have a vapors of, so I have the small zinc oxide already there on this plate. Now what happens is I'm blowing zinc oxide vapors. Okay, it's all coming along in this. They are trying to settle on this. Now what will happen? To the zinc oxide which is there on the surface here and in the vapor, they try to bond better than the zinc oxide vapors bonding on the silicon surface, because they both are dissimilar materials.
Yeah.
Okay. Do you understand? The same materials try to bond together well. So what happens, as time goes, suppose this is the place where zinc oxide was there, I am a new zinc oxide molecule, I stand over it. I am also again a zinc oxide, another fellow stand over it. So you can see that zinc oxide is just growing in one point. Can you imagine this? Yeah. Yeah.
Is it agglomerating?
Agglomeration can actually expand everywhere. There is one more growing like this, they hug each other, it becomes like that. It can also happen. Okay, but imagine that the surfaces are very clear. So this is zinc oxide surface, I am also zinc oxide fellow, another fellow standing, it is just growing on the top. Can you imagine this? Yeah? So you can see that a one-dimensional structure is just getting deposited and growing up. A nanowire is formed.
So why do you need the silicon again?
The silicon is just a substrate.
Okay.
Silicon is a substrate where you want to make it. I'm just giving an example. Most of the electronics are made of silicon. Okay?
Can we control the...
Yes, I'm going to, yes. Okay. So the idea, this is the idea of the nanowire. Now how this happens in the CVD, I'm just taking our own example. So the same quartz tube, so this I opened mainly to show the result, maybe I'll first explain it. So we also, what we did, we had a gas cylinder which had only air, purified air, just air, okay? And we had an argon cylinder. So in air, 21% is oxygen. 21% is oxygen. And the other end open is also an atmosphere, so oxygen is more there. Okay? So what we did, we placed the zinc powder here. We placed the zinc powder, zinc metal, powder of zinc metal. Now you heat this at 670 degrees centigrade. That's well above the melting point of the zinc metal itself. When you heat this all over, what happens is the vapors of zinc is already formed. Yeah? The zincs are, now it's not zinc oxide, it is zinc alone. Now what you're doing, you're passing the air also, which has oxygen, and we have an argon carrier gas, so we say that we call it as 250 SCCM. This is the unit for the flow. And this is something around 5 SCCM, small flow of air. We try to send, we send this kind of gaseous mixture inside. The oxygen in the air reacted with the zinc. Immediately, somewhere at this point, it became zinc oxide molecule. The zinc got mixed with this oxygen in this air and became zinc oxide. And all these molecules, they traveled all the way on that surface. Now I'm zooming this alone. Huh? On this surface, the zinc oxide started getting settled like this. But what happened? This is substrate. It's actually trying to form a film. It will form a film by nature. The zinc oxide film is forming, but the temperature what we maintain here is 670 degrees centigrade around. It's a very high temperature. What I told you in high temperature, we make annealing. The surface will get annealed. So at the very first few minutes of the experiment, when the first 1 or 2 layers itself, the layer forms and it gets annealed by itself. Yeah? So whatever this layer, we call this as the seed layer. The very first layer which forms, we call this as a seed layer. So a seed layer forms, and as a little more continuous time, we actually ended up with making these nanowires. A very high, vertically grown bunch of wires. Okay. So these wires, now on the silicon and grown on this, now this can be used as a Schottky diode for making UV sensors, for making a solar cell, whatever the application can be.
So will the zinc oxide on the substrate evaporate also? Will the zinc oxide on the...
No, this is actually, come again?
The zinc oxide on the substrate.
No, that is the place where it's already getting seeded and it is actually growing.
But so at that temperature will
Okay,
it...
that is a good question. The zinc melting point is different. The zinc oxide melting point is different. Zinc oxide has a larger melting point compared to, so there is no vapors of zinc oxide can evolve.
So can you control the temperature for
Yes.
each section?
So if you see this formula again, so all depends on these formulas. So that if you control this flow, combination of this flow, so this flow decides what is the concentration of oxygen you need. Now if I want to make a zinc oxide, that means zinc should be 50%, oxygen should be 50%. So this is an ACM picture actually, it shows how it is. So by controlling this air here, we control how much oxygen I am going to supply for this. More oxygen if I supply, then it will become ZnO3 or something else. Less oxygen, it will be something else. We saw that also in our experiments. When we had different you can see that when we had less, it's something else. If it is more, he said that agglomeration, lot of friends joined together. That's also a problem. We don't make a nanowire at that time. So after which, probably this is the exactly we are also going to do in our labs. We are going to do this IV characteristics. That's why I started teaching this topic related to the lab. You will see that here. I'm just showing you the IV characteristics. So let's not worry about this figure alone. If you see when we change the voltage, input voltage, now this is connected like a Schottky diode. That means the silicon substrate, the wires, and above the wires we have another top electrode. Okay, it's a diode actually. Zinc oxide is, there are two semiconductors we are attached together, and then when we do a same IV characteristics like what you do with your diodes, basically we've made a diode now with this. If you do this, the characteristics only you see the forward biases. The green color circles is time when you shine the UV, and the blue color one is when there is no UV. You can see the difference in their characteristics. That's because of the change in the resistance of this material. Okay, so exactly we will see this in our labs in the next coming weeks. Okay. So the point here is I want discussing about the application of the CVD system. I showed you how a meaningful deposition for a device application purpose. So some people actually, instead of having this actually is a quite difficult experiment because initially there is nothing. The formation of this seed layer seems to be a very important step. This was really tough. You might have done, I think, Rajay and Trivik, they might have done some hundreds of experiments to come to this point. But people have tried to. They also tried to coat gold surfaces, some gold nanostructures. Okay, say imagine you make a lot of gold dots on the surface of order of nanometers. Now what happens is this zinc oxide is a little biased. It's not only bonds with gold, it also bonds with some metals easily. So zinc oxide and gold, they can bind very well. So at the beginning itself, if you have exactly, imagine these all are, the dark ones are gold, then the zinc oxide will just go and sit there and they form wires. So this also, they say that, they say metal catalyst grow nanowires. Coming back to the slides.
So, how do they prevent
Okay, I mean, if agglomeration happens, means we cannot do anything. You have to do the experiment in such a way that we don't go to that point. Yeah. So once if that's the thing. If the material scientists may not that much worry about the way how the structure is. When we make an electronic device, it should work every time the same. You make hundreds of that electronic chip, it has to work. All the hundreds should work the same way. If it is an Apple laptop, all should be Apple laptop. It cannot be different. So that's a big challenge also. Right. So the next one is oxidation. So this I'll take and then I'll
I have
stop.
a question. Like just now in the lab, you said that the CVD has different sections, right? Like 4 different coils. Can you control the temperature?
Yes, you can control
each
the
one?
temperature of all the 4 and the different values. You can do it. Yeah. But usually we try to keep the temperature almost the same. But practically it won't be same. Some difference will be there. So those are some experimental corrections to do. Okay. One is this chemical vapor deposition. Another one is oxidation. So oxidation is if you take the transistor manufacturing, silicon dioxide is the oxide layer that has to be made. So the gate oxide is silicon dioxide. The FET drawing, which I have drawn many times. There's a gate oxide, right? Yeah? Yes? Yes or no? There's a gate oxide, right? Why are you silent now? Getting bored. So in the transistor circuit, I said that there are two N-well regions, P substrate. We actually have an oxide layer, which is an insulator. Then only you have the conductor here, the metal. Okay. So since this dielectric medium, if you apply a positive voltage, you induce negative voltage, and then you produce the channel. So making an oxide layer in a silicon is a very important step in electronic industry. Okay. In the wafer, if you want thousands of such transistors, then 1,000 regions you should make these oxide layers. Yeah. So how do we make that? So that is made through this CVD system. But here we call the same CVD system as oxidation. Okay. Just because always the reactant gas is always oxygen. So what happens is the wafers are placed like in cassette, a lot of wafers are placed. Say we have resistor heaters along the two tubes. Now the important point here is what happens. The first step, the same system. So that's why I'm not going into details of this again. I'm trying to relate from the same CVD system. Imagine that we don't have any argon or something now. It's just only oxygen or sometimes steam. These are the two. So the first step, what happens? We have the oxygen species, and the silicon substrate is already at a very high temperature. Huh? It's already around in maybe a few hundreds of degrees centigrade. So this oxygen, they first. So how rusting also happens? The rust, if you see the steel pipe, the first surface of this becomes oxide. And you see the rust here because of oxygen reaction. Same thing, what happens? This is at high temperature. So the oxygen molecules, just at the surface only, these oxygen molecules, they react at the top surface of the silicon wafer. Then this top surface, just the first one molecule layer, all the silicon molecules turns into silicon dioxide. The same wafer, which is of 500 micrometer thick, but only at the first one molecule length becomes silicon dioxide. Do you get this, what I'm trying to say? It's like that if I have a beaker full of water, I just put a very micro drop of an ink. So only at the top of the layer of that water is slightly blue in color. Only the top layer is reacted. Yeah, same thing here. The surface of the wafer, the oxygen reacts and becomes silicon dioxide. Now since this is undergoing a heating process, the newly formed silicon dioxide from the silicon, they slowly diffuse inside the substrate. They just slowly diffuse into the substrate. And what happens is, as time goes, if you do more reaction, new silicon dioxide layer forms on the surface. Simultaneously, the formed silicon dioxide layer diffuses inside the substrate. So in this case, there is no actual deposition is not happening. Rather, a reaction at the surface and then a diffusion. So the thickness of this wafer does not grow here. Correct? Do you understand? The thickness of the substrate doesn't grow. It's just the top layer of the surface getting modified to silicon dioxide. So basically, how long this is done? So okay, they have done. I will just leave it to you to read all these slides. I'm going through. So the color, actually, for example, that when they have a 0.39 micrometer thick of, that is 390 nanometers, it has an yellow color. I think we have some silicon dioxide in our labs also. I tried to keep it. It is a green color one. So green color one is somewhere here. This 0.5 micrometer. So depending upon how much thick oxide you want for your transistor, you make that deposition there. say 0.05 or 0.75. So it depends upon the time of reaction. So there are again some formulas there, which again is derived empirically. So that's actually an oxidation. Quickly, can it take another 5 minutes? Or you want me to stop? How many of you want me to stop? Only one. He's the culprit. How many of you want me to continue? Okay. Can I continue? I'll just continue for 5 minutes. Huh? I'm also tired like you. But just I want to finish the CVD part, so I don't want to touch that again. So the last is the. So I was talking about. Okay, before I start, I'll compile what I was saying till now. So I was talking about, guys. Please, I'll finish. Chemical vapor deposition. I was talking about. It's actually one of the very important technique to do deposition. So when we have this kind of a setup with the reactant, there is a gaseous mixes, it reacts, and then the molecules of the vapor states are deposited on the substrate. The overall idea is that. Same system can be used at one end of the tube, can be maintained at atmosphere pressure or at vacuum pressure. We call it as low pressure or atmosphere pressure type of CVD. Another one is oxidation, which is only specifically for making oxide layers on silicon. The last one I'm going to talk about is the plasma enhanced vapor deposition. We call it as PVCVD. So I just want to tell what is this plasma is all about, and then I stop. Okay, how many of you, because nowadays there is a lot of computer games. I lost the knowledge of these computer games now. Nowadays I'm not playing. You know, my favorite computer games when I was in my undergraduate was Age of Empires. How many of you play still? Okay, I used to play Age of Empires. The first Age of Empires was some Roman. That one looks very childish now. It's very simple one. Then came Age of Kings 2. Then the Age of Mythology came. And then now they're very recent, then very advanced Age of Empires have come after that. Then it became so. I used to be so crazy. Whenever the lecturer used to teach, I used to think back in home. I'll go and do this, then I'll finish that fellow. So that was physically I was present, mentally I was absent actually. Another interesting game I used to play was, I don't know whether that game is still there. Quake 3. Quake 3. Is it Quake 3? Quake 3, is it still there?
Yeah.
Huh? It's still there. Huh? So the Quake 3 one, the game goes like this. There will be some bots going here and there. You have to just shoot all of them. Yeah? Crazy game. So there is one gun is there. There is one special gun is there. It's called plasma gun. Plasma gun. You shoot it. The pink color comes. Shoot. Just pinkish color comes out. Yeah? That's a very nice one. But that's the plasma gun there. But what is actually plasma? I'll tell you now. Okay. So plasma is yeah. So at a very high voltage, okay, and yes, at a high voltage, and say you have an inert atmosphere. Yeah, guys, please. At an inert gaseous atmosphere, say argon. Argon is an inert gas. So molecules of argon is all around. Except argon, nothing is there. Imagine like that. And then we have a very strong high voltage between them. So what happens is, these argon gas molecules, they get positively charged or ionized because of the electric potential, high voltage. This could be DC or AC. So all the argon molecules inside, they get ionized and they have a very high electric energy potential. They have very high energy. They're very fast to move now inside. They have very high kinetic energy because of their ionization. So what happens is, this argon, this energy, whatever was there, So that is also little released in terms of some light, and that wavelength is in the pink color. That's why it's pinkish in color plasma if you use an argon. Okay. So what happens? These high energy molecules, when you have a metal target facing this, say suppose there is a source which produces these ions and ionousness, and this metal and these argon molecules, if they go and strike this metal target, so when it is going and striking it at that high kinetic energy, the exchange of this energy, this kinetic energy, it develops at that molecule size of a very large heat, and it evaporates that molecule size of a particle from the target. You understand what I'm trying to say? Something goes very so fast and hits the surface. When it hits that surface, the molecule in that surface is actually getting some heat energy and it vaporizes. There is no heating element anywhere, but it's because of the ionized argon molecules going and hitting the target molecule vaporizes. So see, this is one molecule. Imagine there is a millions of molecules going and hitting it. We call it as bombarding. Like how I'm going to ask question in final exam. Bombarding the questions. Like this, we bombard the question, the molecules plus the surface of the target will vaporize. So once they are vaporized, say this is the metal, so we now have metal ions everywhere flowing around. Now when you have a substrate underneath, these metal layers, they just condense on that to form a layer. Okay, so PECVD, in addition to we don't have the gases, but we have this plasma inside to make the same deposition. Then we call it as a PVCVD. Okay, yes.
Where does the plasma come in again?
With respect to CVD or generally?
No, in the CVD.
I mean, in the CVD system, instead of this heating coils, probably you have we don't now vaporize that material because of heat, rather because we vaporize by plasma. Now when we have plasma, we don't have any heating coils.
So
We don't, I mean to say that you don't want a high temperature system to evaporate. Instead of heating, I'm evaporating by plasma.
So the plasma is actually the ionized argon.
Ionized argon, yes. Okay, so this is not I should not tell this, but it's an analogy to think on sublimation. If you heard of this, camphor, when you heat it, it just doesn't go to liquid but evaporates to vapor. Yeah. So it's not the same, but I'm just giving an analogy for this. So this is like the plasma hits the surface without heating, the surface is getting vaporized. Okay, so that's the PVCVD. I think rest all you can read from the slides.
So you can direct. Basically, you're directing the plasma. Does it have
Yes.
a white spray?
Yeah, it will have a white spray. Depends on the
Then won't it
diameter of
affect the substrate?
Yeah, once the material is vaporized, say in the same tube, in the previous picture what I have, so it's going to be there everywhere. So in this case, maybe they may not use the tube what I showed
No,
you.
so I'm
They
saying-
may have a vertical tube.
No, like you said, the plasma spray. Can it be directed, or does it come out as like a spray, like a?
From the source, it just comes out.
Or will
Like
it?
a torchlight.
Won't it vaporize the substrate also?
Huh?
Won't it vaporize the substrate also?
What it vaporizes the substrate. If you focus on that, maybe yes. But usually we target the metal. The metal will react and vaporizes. We don't keep the.
So the metal plate, is it also charged?
Huh?
The metal plate, is it
No.
charged?
Imagine that these things all happens in a small tube, like a torchlight. Okay. Imagine like this. All this happens in the torchlight. What is coming out is only the plasma light. After that, only we have our things like that. I think you can see this in your lab also.
What's the power source for? The AC source?
If you don't have the power source, how do you ionize the gas molecules? So this power source ionizes the argon. Yeah. So either it should be a very high voltage
Okay, so the two electrodes, one is the argon electrode that's being ionized. Is it?
I mean, this is just the 2 electrodes. You are supplying the power. Imagine there is a gaseous atmosphere.
Of argon.
Just argon. You vacuum everything, then you put only argon inside. Then you.
But so how do you direct it towards the metal? Because the atmosphere is like basically the air in there is argon. How do you direct it towards the metal?
But we don't direct it, it's just already there.
But then,
It's a small chamber, it reacts everywhere. Imagine that I put a jar like this, it reacts everywhere.
but then won't the substrate also get affected?
Talk alone.
Huh?
We will talk together in the lab then. Okay. Okay, so I stop here. So some slides I have skipped, it's just for you to read yourself. But I am just only giving the main ideas.
So in the example of the zinc oxide,
Yes, I may ask. If I teach, that means I may ask.
I mean, but you know, annealing is a very random process, right?
Listen.
Annealing is a very random.
Come again?
Annealing.
Any?
Annealing.
It's a very random process, right? So you can't really control how the virus will be. For example, the distance between the virus.
Yeah. If you maintain certain distance between the substrate and the source, and if you maintain the right flow, and if you maintain all the experiment parameters, then you definitely will get. That's what it's very hard to get as well.
No, he's talking about the distance between the nanowires.
Distance between the 2 nanowires? Good question. That we don't have much control.
So then the IV characteristics of to some.
But when you use this step, every time when you do, you will get the same. Now, if you want to have if you want to make a distance between these two, you want to assign, then you have to coat the gold. I told you, right? So people do that. They do an E-beam lithography of this, and they can exactly grow in what places. These are all now current research. They But right now, it's we have this kind of things.
Both of them.
This is a very recent work, last year. Okay, so I think it's